Last time we started talking about arithmetic combinations of functions, and we also talked a little bit about how we can find the domain of those combined functions. Today we're going to talk about composition of functions, really plugging one function into another function, and then we'll also talk about decomposition of functions as well. So composition of functions is plugging one function into another. Another way to think of this is that the output of one function becomes the input of another function. Now for composition in terms of notation, we denote it using this symbol here. It's not quite an O, it looks more like a degree symbol, but it's more in the middle than it is further up where the degree symbol normally is. So this f of g of x is how we would say it, f of g of x is equal to f parentheses g of x. So this other way of writing it denotes that whichever function comes after that symbol is the inner function, and whichever function comes before it is going to be the outer function. Here's example 1. Given f of x is equal to the square root of x and g of x is equal to x minus 1, x is greater than or equal to 0. And we have that restriction there because we have that square root of x already there. So x has to be greater than or equal to 0. Find f composed with g of x and g composed with f of x, or f of g of x and g of f of x. So f composed with g of x, that means that g is the inner function and f is the outer function. So we are going to take that x minus 1 and we are going to put that in as our input into our outer function, which is the square root of x. So this becomes the square root of x minus 1. All right, for the second one, g composed with f. Now f is the inner function and g is the outer function. So the inner function being the square root of x. And now we plug the square root of x into our function g of x, which is x minus 1. So instead of the x, we are going to write the square root of x minus 1. And so you can see the difference between those. One has the minus 1 inside the square root, one has the minus 1 outside of the square root, just to clarify. Now the domain of a composed function is a little more complicated than talking about the domain of an arithmetically combined function. So a couple things to know. First, all real numbers that are in the domain of the result will be in the domain of the composed function. Second, all real numbers that are in the domain of the inner function only will be in the domain. So restrictions only carry through from the inner function, not the outer. Let's take a look at example 2. So here we are finding the composition of f and g in both directions, as well as their domains. So let's start with f composed with g. So this means that the inner function is g. So I'm plugging in 4 minus x squared into my function f. So this will be 4 minus x squared plus 2. And we can simplify that down, and that becomes 6 minus x squared. Now for the domain, you're looking at two things. You're looking at the resulting function, so 6 minus x squared. Are there any restrictions on 6 minus x squared? Are there any square roots? Are there any denominators? It doesn't look like that in this case, so this is going to be all real numbers. Okay, and then we look at the inner function. The inner function is g of x. That's the 4 minus x squared. No square roots, no denominators, so our domain is going to be all real numbers. So we combine those two domains, the most restrictive, but in this case, because it's all real numbers for both, our domain is going to be from negative infinity to infinity. Let's do it the other way around, g composed with f. So this means that f is the inner function, g is the outer function. So we are plugging in x plus 2 into our function g. So this would be 4 minus parentheses x plus 2 squared. And then if we're going to multiply this all out, we have x squared plus 4x plus 4 and then we subtract that, we combine like terms, we should end up with, well, the 4 and the minus 4 cancel each other out, so we're left with negative x squared minus 4x for our resulting function. And then again, for the domain, you are checking the resulting function, negative x squared minus 4x. Looks like there are no restrictions there. And then you are checking the inner function, which is f of x. So x plus 2, were there any restrictions there? No. So the domain here, combine those two, and the domain is going to be negative infinity to infinity. Okay, so now let's look at a more interesting example. Let's say f of x is equal to x squared minus 9, and g of x is equal to the square root of 9 minus x squared. So find the composed functions f composed with g and g composed with f. So first, let's do f composed with g. That means g is the inner function. So that means we're plugging in the square root of 9 minus x squared into my function f. So we are plugging this square root 9 minus x squared in for x in x squared minus 9. So this becomes this whole thing squared minus 9. Let's simplify that, and we get 9 minus x squared minus 9. The 9 and the minus 9 cancel. You're left with negative x squared. Now let's talk about the domain. So the domain, again, you want to check two things. You want to check the domain of the resulting function and the domain of the inner function. So in this case, the domain of the resulting function, negative x squared, looks like it can be all real numbers, right? No restrictions, no square roots, no denominators in that resulting function. Next, check the domain of the inner function. So the inner function in this case is g of x, which is the square root of 9 minus x squared. Okay, this one we definitely have a restriction because we have a square root in there. So what's under the square root has to be greater than or equal to 0. So 9 minus x squared is greater than or equal to 0. Now, in order to determine exactly what that domain is, let's think about what this looks like. Right, so you're looking at 9 minus x squared, which is a quadratic, which is a parabola facing down. And where are the roots of this function? Well, if we were to factor this out, this would be 3 plus x and 3 minus x, which tells you that the roots are at 3 and at negative 3. So drawing out this function, we said it's a parabola facing down with roots at 3 and negative 3. And so where on this function is your y value greater than or equal to 0? Well, it's greater than or equal to 0 anywhere starting from the x-axis and above. So this part right here that I've highlighted in green, and including 3 and negative 3 because it's equal to 0 at those points, which is fine. So the domain restriction here is that it has to be between negative 3 and 3 inclusive. Now the domain of the entire function, right, we found the domain of the resulting function, the domain of the inner function, and now we have to combine them, and the most restrictive result is going to be the domain of this composed function. In this case, because the first one, the domain of the resulting function, is from negative infinity to infinity, not restrictive at all, and the domain of the inner function was much more restrictive, then we take that, negative 3 to 3, and that is going to be the domain of our composed function here. So although it's not obvious here that negative x squared would have domain restrictions, it's because this is a combination of two functions by composition. So the domain is going to have to be restricted between negative 3 and 3 because of the inner function. Okay, now we've only done it one way. We've only done f composed with g, so now let's do g composed with f. So g composed with f of x, that means f is the inner function, so we're plugging in x squared minus 9 into g. So this is going to end up being the square root of 9 minus, parentheses, x squared minus 9 squared. And if we are going to Multiply this all out, we'll end up with 9 minus x to the fourth minus 18x squared plus 81. Simplifying that, we have the square root of negative x to the fourth plus 18x squared minus 72. Now, we have to check and see what the domain is. So again, checking two things. You are checking the domain of the resulting function and the domain of the inner function. So let's start with the domain of the resulting function. So the domain of the resulting function, we have a square root for sure, so anything that's under the square root has to be greater than or equal to 0. Now to factor this, I'm going to start by factoring out a negative sign. This way, now I can just work with the x to the fourth minus 18x squared plus 72, and this actually factors to x squared minus 12, x squared minus 6, and then because these are still not linear factors, we have to take each of these and set them equal to 0 to figure out where the roots are. So this would be x is equal to plus or minus the square root of 12 plus or minus the square root of 6. Now you can obviously simplify the square root of 12 down to 2 root 3. I'm just going to leave it as a square root of 12 for our purposes here. So for now, let's just see what this graph looks like. Now this is a graph of degree 4, and we have 4 roots at negative root 12, negative root 6, positive root 6, and positive root 12. Because it's degree 4, we have all 4 of the roots found, and because we have a negative leading coefficient, we know that on either end, the end behavior of the function is going to be down and down. And so it's going to be down on the left, it's going to go through negative root 12, then go through negative root 6, then back up through root 6, and then back down through root 12. Now the original inequality that we had written was that this function must be greater than or equal to 0. So you want to look at your graph and see where is it equal to and above the x-axis. And that would be this section here and this section here. Okay, so to state the domain of the resulting function, it would be from negative 2 root 3. I'm going to change it to its simplified form. Square root of 12 is 2 root 3. So from negative 2 root 3 to negative root 6, including those values, and then from root 6 to positive 2 root 3, including those values. Now we have to check the domain of the inner function. So the inner function in this case was f of x. That was x squared minus 9. And so looking at x squared minus 9, there are no square roots and no denominators, and so the domain of the inner function is from negative infinity to infinity. So now, combining both of those domains that we found, whatever is the most restrictive, combining the two, is going to be the domain of our resulting function. So this is going to be from negative 2 root 3 to negative root 6 inclusive, and then from root 6 to positive 2 root 3 inclusive. Okay, so now let's talk about decomposition. We've spent so much time talking about composition of functions. Let's talk about decomposition. So decomposition of functions is writing one function as the composition of two different functions. So taking one function and basically breaking it down into two, or it could be even more functions. So in example 4, write h of x equals 1 over x minus 2 squared as the composition of two functions, f of x and g of x. So here's what I like to do when I try to come up with the decomposition of a function. So here's h of x, and I'm going to pick what my inner function is going to equal. So let's say I pick the part that's in parentheses, the x minus 2. In that case, that means that the inner function is x minus 2. Let's say g of x is the inner function. And then the outer function, what does the outer function have to be? Take whatever you circled, and if you make that part that's circled an x, that tells you what the outer function is. It would be 1 over x squared. So in this case, g of x is equal to x minus 2, and then my outer function is f of x, which is equal to 1 over x squared. Now, there are multiple ways of decomposing a function. There's not just one correct answer. And so let's just do another example of how we could also decompose this function a different way. So again, here's my function h of x, and let's say instead of just the part that's in parentheses, I take the entire denominator and make that the inner function. So this part right here, I'm going to make that g of x, so g of x is equal to x minus 2 in parentheses squared. And then what is my outer function? Well, I'll take the part that I've circled and I change that into an x, so that makes the outer function f of x equal 1 over x. So again, there can be multiple ways to decompose functions. The important thing is that when you do compose those functions, you can double check and make sure that you are in fact getting back that function h of x and that you've decomposed it correctly. So although there are multiple solutions, there are also ways of doing it incorrectly. So you want to make sure that what you are doing is in fact decomposing it accurately.